Hello. Hi guys, good morning. Welcome back to a new video. In this one's problem number 4 of today's weekly contest 392. Minimum cost walk in a weighted graph. This contest had one of the worst problem statements, and I guess some bit of cheating also happened. I'll not say how much, but considering it was, see, in this problem also one edge case is there, which there is nothing mentioned ki how to tackle that edge case. You will first have to do a wrong submission, or maybe you have to guess and then get the edge case. And in the third problem, it was completely wrong. We will see. Cool. It says that you are given an undivided weighted graph. Usually when we have given an undivided weighted graph, which means we are given a u to v edge, and that edge will have a weight, which is w. Now you have to tell, again, that's a very specific thing. You have to tell a walk on the graph is a sequence of vertices and edges. The walk starts and ends with a vertex, and each edge connects the vertex that comes before it, and which means a walk is such that, okay, if I ask you to walk from 0 to 3, then you can walk any way whatsoever. You can walk 0, 1, 3. Okay, that's a one walk. And walk can be, okay, 0, 1, 2, 1, 0, 1, 3, 1, 3, 0, 2, 1, 3. It's also a walk. Walk is simply like you are randomly going and walking. That is a walk which is represented. Now, the cost of a walk is nothing but all the weights. You remember that, okay, when I did a walk, okay, from 0 to 3, when I did a walk, I went on, okay, 0 to 1 and to 3. So 0 to 1 I went on, I incurred a weight. Basically, I encountered a weight of 7. So that all the weights which I'm encountering, which means all the edges which I'm encountering while walking, I'll do a AND operation on these weights, or basically on these edges weights, and that will be my walk cost. So if I go here from here to here, then you can see I encountered 7 and 7. So I'll do a 7 and 7. Again, that's an AND operation, bitwise AND operation. If I ask you, what is the speciality of bitwise AND operation? First speciality is that 1 and 1, it's a 1. 1 and 0, it's a 0. 0 and 1, it's also a 0. 0 and 0, it's also a 0. Which indicates that if I do a bitwise AND of two numbers, it will always either remain same or will decrease. That's it. Bitwise AND of two numbers, if I do a and b, because of the operation, that AND operation will only result one when both of them are available. So if I have, let's say, a as something, b as something, then if I want, okay, this to be a 1, so for sure this should be a 1 and this should also be a 1. If let's say it is a 1, it's a 0, it will be for sure 0. If it's a 1, it's a 0, it will be a 0. If it's a 0, 0, it will be a 0. So you will see that a is something like this, b is like this, c, basically the AND operation between a and b will be less than a and b, or can be equal to either a or b, but AND operation will never be more. That is a very big hint for this problem, that AND operation always reduces the value. Aryan, why are you telling this? Because first thing, before even going forward, you should remember what AND operation does. OR operation, your value can increase. Value can increase. In AND operation, value can or cannot decrease. As in, like, it will or will not decrease for AND operation value. Which means, let's say if I would have a 1. So you will see the AND operation you would have achieved AND operation of 1, 1, 0, 0. So it is same as that of A. Let's say if I would have a 0 here, so again it is same as that of V also. So that is the case. Let's say if it would have been a 0, if it would have been a 1, 0 and a 1. Or let's say here is a 1, here is 0. So you will see I'll get an AND operation as 0, 1, 0. So now I got a value of B. So that's a simple crux, is that AND value just decreases. Maybe can be same also with any of these value, all will be less, but it will never be more. With OR, I can get same or more. So it's opposite. Now coming on back to what I wanted, okay, I showed you what's the cost. Cost is the weight of the path which you will take. Then you will take the AND operation of that path. So let's say here I took a path from here to here, then AND operation was 7 and 7. What if I took a weight, okay, 0, 1, 2, 1, 0, 1, 3, then 7 and 1 and 7 and 1 and 7. So that is the weight. That's the cost which I will be taking. And you can see, as more number will keep on coming in, my cost will keep on reducing. That's the main thing, that you are given a 2D array called as queries, and ultimately queries says from SI to TI, which means from this source to this destination, SI to TI, you have to go and travel. For each query, you need to find the minimum cost of the walk. You have to find the minimum cost, which means you have to minimize this AND operation. You have to minimize the AND operation, and this AND operation you have to take the weights, weight of I of 1, weight of I of 2, and so on and so forth. So as to minimize the AND value, the best strategy is to take as many AND combinations as possible, which means if you have option, then try to take as many ANDs as possible. As many AND will give you the minimum cost, minimum AND result finally, because we realized that more the ANDs, more chances of thing being decreasing. And ultimately I have to return for every query, I have to return what is the minimum cost for each query. For example, in this case, if we take on, okay, my first query is from 0 to 3. I have to travel from 0 to 3. Then I realized I have to take as many AND as possible. So what I will do, okay, I know AND I will take off these weights. Of these weights I will take. So I will do one thing. I know I should take as many ANDs. How many ANDs I have? I have only 3 ANDs. 7, 7 and 1. So I will take all of them. So I'll say, okay, 7 and 7 and 1. That is the maximum number of values I can take. Different values to reach from 0 to 3. So I'll take all these ANDs. What will give? This will give, okay, 7 is 7. If I represent, it will be 1, 1, 1. Again, the number 7 is 1, 1, 1. Again, the number 1 is 0, 0, 1. So you get a 1 as the AND operation. And thus, from 0 to 3, I can go, because I know this is in one component. This is 0 to 3 is in one component. Both are connected. So I can anywhere roam around, anywhere whatsoever in the entire component, and then can go to 3. So I took the benefit of all the weights in that component and reached my final answer, which is 1. So the cost to travel from 0 to 3 will be nothing but 1. As you can see, 1. Now, okay, 3 to 4. 3 to 4. You cannot even travel from 3 to 4. Now, the question splits. One part of the question you have solved. With this first query, if I just simply erase this, with this first query, you have solved one part of the problem, that your weights, to minimize your cost, you will have to take the AND of all the weights in that component. So if I ask you to travel from 0 to 2, cost will be still 1. To travel from 1 to 3, cost will be still 1. To travel from 3 to 2, cost will be still 1. Right? So I realized, okay, Aryan, things seem sorted, that to minimize the cost, or basically to get the cost of any travel between any nodes of this component, I will take the AND of all the weights in this component itself. Aryan, what are you doing? Find component. If you don't know, finding a component, if you don't know how to find it, that can be simply found by either both DFS or BFS or DSU. I don't recommend DSU in these cases because, again, it's a big code, a bit big code. DFS lines of code are 5, DSU lines of code are 15. That's the reason I usually don't recommend. Wherever you can use DFS or BFS, use that. If not, then use DSU. If you don't know Aryan how to find component, just write down component, find component in a graph by Aryan Mittal, or go and visit Bob Graph series. You will get it. Now, coming on back, the issue was, Aryan, we got this, but what about this? Oh, you will see that you have to identify if two nodes are in the same component or not. How will you do that? Simply number the nodes. How to number the nodes? Simply, when you will do the DFS traversal to find the nodes in that component itself, while doing that, number the nodes. Okay, this node is of first component, so I will start my DFS. If you forgot, I'm just simply finding the components, and I'm saying, okay, I'm starting my DFS from the node 0, and initially my component number is 1. So it is the first component. So all the nodes of the first component which I will be traversing, I will mark, okay, this node belongs to first component. Okay, I am doing a traversing starting from 0. Okay, DFS, simple DFS. Now component number of node 0 is 1. Component number of node 1 is 1. Component number of node 2 is 1. Component number of node 3 is 1. Okay, this component is done. I cannot traverse any further. It's a simple DFS traversal. Now, again, but still, you will try for the next node. Next node 1, it is already visited. Move on. Next node 2, already visited. Move on. Next node 3, already visited. Move on. Next node 4, not visited. Okay, no worries. Increase the component. Now, the component number will be 2. It is the next component which I am trying to traverse. Okay, so I'll just traverse it. Oh, starting, I visited, it is finished. But I numbered this component as 2. So I realized, if by this I have marked every node and their corresponding component. Every node and their corresponding component. if the components are even different, which means they can never be connected. If two nodes can never be connected, I can never walk from this node to this node. That's the reason the cost will always be -1. So in my query, I know, let's say if it is I, it is j. If I know the component of I, if it is not equal to component of j, I can never traverse between these two components. So answer for that specific index, let's say id, which means answer for that specific query, which means answer of id will for sure be a 0. Sorry, for sure be a -1, because you can see -1. Now for the more simplicity, like for the next example, let's look at the example. I've traveled from 1 to 2. 1 to 2. Again, I'll do one thing. I'll simply find. Okay, firstly I have to check both are the same component or not. But I'll do a pre-computation. I will simply, in the very beginning itself, I will find, bro, what, okay, this node belongs to what component. So I will do a simple traversal. Okay, as I do a simple DFS from node 0, I'll say my component number in the very beginning is 1. So if I do a DFS traversal, all the nodes will be of component 1. Okay, component 1, component 1, component 1. Okay, my DFS is done, and all of them have been marked as a component of 1. This is the component of 1. All of them belong to component of 1. But Aryan, you are saying that you have queries, and queries are also very large. Like queries are 1e5. So you will do queries answer, like queries answer, you have to get it in O of 1 time. You cannot go and traverse the entire graph again for every query. You cannot do that. So you have to compute. You have to compute. What is the answer for every query? I realized the answer for every query, either it can be a -1 if both of them belong to different component, and component I am actually grabbing, and I will mark for every node what is the component of it. So one thing I will make sure, okay, I have component. What is component of every node? Of every node. I will keep this thing as a pre-computed thing. Okay, what else I need? I have to give the answer. I have to give the answer. Answer is for this query. Oh, which means, and this answer is minimum of what? Cost. And I realized minimum cost is the and of all the nodes, and of all three, and of all the weights, and of all the weights in that component. Okay, so Aryan, you're saying that you will also have to, again, if that you will say that, okay, 1 and 2 both belong to same component, but what is the answer for this query? Answer for this query is, okay, I know that 1 and 2 belong to same component and the component number is 1. I will go and ask, bro, for the component numbered 1, what is the and of all the weights, and of all the weights for that component? So I'll say, bro, okay, now my task is to find and of all weights in that component. That is my task now. So how I can do this? Simple, bro, simple. You know that this node, you know that this node belongs to a component of 1. For sure, if I have my input as in this, I have this query as an input. I will iterate on this query. I will iterate on this entire query and I'll say, okay, bro, component of 0. What is the component of 0? I simply ask because I have mapped already. What is the component of 0? I know. I'll grab the component of 0. Component of 0 will be 1. So I will say, bro, okay, I know that for every component I have to find, okay, in that component what is the and of all the weights. So I have to do the and of all the weights. So Aryan, are you saying that, okay, you will have a map, basically you will have, okay, for that component, which means component, let's say component and value. So this will keep track of for that component what is the and value. So right now for me the component is 1. The component is 1 because this node 0 belong to component 1. So what is the and value which I can get? I'll simply say, bro, and value of what? Of the weights. So I'll simply take the weight. Okay, this is the weight which I will take, and I should do the and. Okay, I'll do the and operation. I'll do the simple and operation. But Aryan, what about this node 2? You have, like, bro, if you and if this node 0 and node 2 are connected, for sure both will be in the same component, right? So this will also be in the component 1. So I'm just getting the value of component 1. Okay, component 1, what is the contribution of a weight? And that I will keep on adding. But Aryan, this is the and operation. which means that you will have to by default initialize it with something. You cannot initialize with a 0. Component and value of this component number 1, this is a component number, you will have to initialize it with something. You cannot initialize with 0 because it's an AND operation, and will keep on decreasing it, and if it is 0, it is already decreased. So what to do? I'll say, bro, yeah, you are absolutely correct. So I have to initialize with a very high value. What is the highest value I can have? I'll go back and see what is the weight highest value. It is 1e5. Okay, so any value which is more than 1e5, but I cannot take, okay, 1e5 plus 1, because it is, I'm doing a bitwise AND. So I want, okay, how many bits this number can take? 1e5. Yeah, how many bits this number can take? If we go and check how many bits this will take, if I click on this, where is this gone? Yeah, 2 raised to the power, let's say 23. So it is 1 2 3 1 2 3 6. So I will say 20 bits. 20 bits it will take. Okay, or let's say 20. If I do 20, so it is 1e 1 2 3 1 2. See, okay, for sure 20 bits at least. Like everything will be done in this 20 bits. So I know that 20 bits number will be taking. I am doing a bitwise AND. So I realize that bitwise AND I'm doing, I have to initialize this with a default value. So why not initialize with a all 1 1 1 1 1, all 20 bits as 1, right? That I will do. Again, for safety, you can take 32 bits also, 32 bits or like 31 bits. Very safe, 1e9. But okay, but realistically, you can take 20 bits and that will work. All 20 bits should be initialized to 1. And then I will go on the entire edges and will check for that component what is the minimum weight. Well, basically, I'm minimizing the AND operation of the weights. So I will just say, okay, component value of this component number 1. Okay, do AND operation of the current weight, which is 7. Then, okay, next edge. Okay, what's the component value? It is 1. It is 1. Okay. Then for the component of 1, again do a AND with 15. Okay, then 1 and 2 both have component of 1. For this component of 1, again do a AND with 6. Okay, for this 1, for this 2, have a component of 1. For this component of 1, again do a AND with 1. Ultimately, as I'm going on in this entire edges, I will be iterating on all the nodes which I would have had, and corresponding to all the nodes, I will be actually getting the corresponding AND value in the corresponding component AND value. So this is a map which will store, again, one is component number, which will say, okay, for every node, what is the component number? So I will have two maps. One map will say for a node, what is the component number? For this node 0, component number is 1. For the node 2, component number is 1. As an example above, for node 4, component number was 2. So one map will store this. Another map will store for component number, what is the AND value of that component. And I'm doing AND value, so I have to initialize with a something that it is by default. So by default, I initialize with all bits as 1. Let's say I'll say 20 bits are enough for me. So I can initialize this all ones of 20 bits. I can say 2 raised to 21 minus 1 will be all bits, all 20 bits having 1 1 1 1. That will be my initialization, which I can do for every of my component and value map, which will say, okay, this is the component number in that. And that's the only answer. Thus, you will know that for every component, what is AND value. Now, if I come back to every query, I will just ask, bro, okay, node 1 belongs to which component? It belongs to component 1. For the component 1, what is the AND value which I have got by the pre-computation? And that's the answer. Cool. Let's see the code. It's not see, the problem statement is easy, but to see the path, okay, oh, this is the thing, oh, this is the thing, this is the thing, this is a bit tricky, and this is what we teach. Link stuff, one after another. That's how we do it. So in the very beginning, I will simply build my graph as I usually how we build the graph. Simply, we require one thing. We require U to V. It's just a graph. V to U, it's an undirected graph. Now we will have node to component, which means for every node, what is their corresponding component number? I will iterate on the all the nodes. I will visit a node. If it is not visited, I'll do a simple DFS traversal. And okay, currently my component number in the very beginning is 1. I will do a DFS traversal for that specific node, and the DFS traversal will keep on going to all the nodes where he can go, and he will say for that node, this is the component number which I have passed in, which I have passed in, and then again simply do a DFS traversal to all the neighbors. Again, if it is not visited, then do a DFS traversal. And for sure, please make sure to visit something if you're visiting it for the first time. So that you don't visit it again and again. That's a simple DFS traversal where you have just added one line in which this line just says that this is a node and corresponding component, I have marked it. Cool. Now with this, as you can see, when one DFS is done, you know that all the components are visited. Then you will increase the component number so as in the next iteration, when the next component will be there, then you will actually be saying, okay, bro, this is the new component number I have. Cool. Now, so far you have stamped for the entire graph. Okay, let's see, this is the graph. So far you have stamped, okay, for all these nodes, component number is 1. For all these nodes, component number is 2. And for all these nodes, component number is, let's say, 3. Let's say 3. So you have stamped this thing, component number, component 2, component 3. For every node you have stamped, okay, this node belongs to what component? Now my task was, the other task was, for this component, what is the AND value of their all weights? So I told you, I will initialize, I will firstly have a map and I will initialize the map with the highest value possible. So I took, okay, again, this is the worst case, but for us, this is very high. I can even take 21, that will still work for me. I showed you why. Then I will initialize and say, and worst case, I can have n components. So I just took n. Although you can take here as component plus 1 also. That also you can easily take. Cool. Then you can simply say that this is component and score, which means for a component, what is its corresponding and score? Cool. Now you will go on to all the edges which you had in the beginning, as I showed you, and then for that node U or node V, again, both node U and node V will have the same component. So I just grabbed the component. What is the component number? What is the component number of the specific node? Right? And then when I have got the specific component number of a node, I will just say, okay, for that component number, the component number, the component score, I'm just doing an AND operation with the weight, edge weight, with the weight, I'm doing an AND operation. With this, as I am going on iterating on all the edges, I will actually be incorporating all the possible weights corresponding to all the components. Cool. And I will simply get, okay, component and score for this component is whatsoever map will give me as a value. Now I will come on to my queries so that I can now finally solve my queries in O of 1 time, because you saw that this will take O of n time to iterate on all the nodes to build their component number. This will take again O of n time, or basically O of m time, m is the edges, to go on to all the edges to build up their score value for that specific component, and ultimately I go on to all the queries. Let's say queries is q. So what will happen if, again, I told you that although by this fashion it seems like everything we have done, but one thing we have missed. What we have missed? We have missed, okay, you remembered that if something belongs to two different components, then I simply say that, okay, the answer is -1. I can just also check that because I have the component number for both the nodes. But if I say if 3 and 3 both are same, then what? Then what? So by the problem statement, it should be 0, which means there is the cost is 0. The cost is 0. Although, like, you can infer that also, but specifically it should have been mentioned, is what I think. So this is one thing that, okay, if both node U and V of query, if both node U and V of the query are same, then the cost is 0. So push back 0 in the answer. If both of them belong to different component, which means if the node to component of the U, node to component of V, if both are different, then your answer is -1. If both are same, then your answer will be stored in the, okay, in the component itself. So this is the U, this will give the component of U, this will give you the score of the component U, right? So again, this is U, this will give you the component, again, sorry, this is U, this is U, this will give you the component of Q, this will give you the score of the component U. And this is the score which you wanted to push in your answer. And ultimately you will get the queries for every answer. So using two maps, two unordered maps or two hash maps, you got your answer, and time will be O of n for the vertices, or I should say vertices plus edges plus your queries, which is Q. And space also, I will say my space will be O of V plus A, and that is your answer. Cool. Thank you for watching. Goodbye. Take care. Bye bye. Question 3, 2, and 1 will also be coming soon. Bye bye.